Oh yeah, good. This one's funky. So 56-1, remember that's with no rotations. Just find the area between two curves. Find the area of the region bounded by the parabola, y equals x squared. And then they get all evil. The tangent line to this parabola at 1, 1. And I think it's the x-axis. Where'd you go? The x-axis. So these are my walls that define my region. So I have to do a little work for this one. They didn't give me the equation. They told me how to get the equation. Like, oh shit, thanks. So this is an old problem. This is an old problem. Good little trick one, aren't you? How do I do that? Do you guys remember that?
Finding derivatives.
Yeah, these days should be nice in retrospect, right? So, tangent line to this parabola. So, what do I have to do first?
Finding derivative.
Find the derivative.
dy dx.
Remember those days? So beautiful in retrospect. All right, and what does that enable me to get?
Slope.
Slope. So, what's the slope at 1?
2.
Yay. So that's m.
So
And I know it goes through the point 1, 1.
y equals.
So what I would do is I do this, I go y equals 2x, and then I go, okay, 2 times 1 is 2. But what do I do that to make it 1?
Minus.
Alright, that's, I don't mess with y minus y1. Shit, that's just extra work. I just go, how do I adjust that to make the output what it's supposed to be? And then you just get there a little quicker, right? Or if you do y minus y1, the whole thing, it's fine. How are you doing like that? I mean, so normally they give me just equations and I have to figure out, who's on top and all kind of stuff. Now they gave me, the second thing they told me was not the equation, I have to make the equation myself. So now we got our walls. We got this one, that's a wall, this is a wall, and the x-axis. Cool. Take a second to try to graph that region if you haven't done this problem already.
But shouldn't we find intercepts for the tangent line?
We already know it,
Okay.
right? It's pretty much, it's given to me. Right, where's this tangent line intercept the parabola? Well, I knew that before I even knew what the tangent line was.
No, I mean x-axis.
Yeah, we'll have to get that. Yes, you better get that. That's the one wall I don't know yet where it meets. So you want to be kind of smart about the scale you use. I know everything's going to happen. 1, 1 is where these things meet, right? So I know my parabola, there it is. Like that big. Let it go, Jeff, sorry. My line, so now what do I need to know about my line? Here's one wall, here's another wall. So like John said, the important thing to find next is where that line hits this wall. And of course, where does it hit that wall?
0.
What's the x-intercept?
1
1/2, there it is. What makes it 0? 1/2. So then it meets there. Sure. So that's my region. Now alright, let me just let you absorb that for a minute, right? This would so suck if your scale was too big, because that is, even my scale, that kind of sliver, right? You want to really show yourself what the hell's going on. Because what's important now is, let me draw it again even a little bigger. So I've got my parabola. Well, I got my line. Well, that's horrible. Will I be able to do this? Let me go, Jen. There we go. So I got this region here. Now notice, so what's, so I've got my, this is y equals x squared. This is y equals 2x minus 1. And this is y equals 0. Those are my walls. Is that cool? And so which function is on top? Well, this gets a little weird because what's always on top? X squared. Y equals x squared. So why do I say it that way? Because what's on the bottom up to what? The bottom, to begin with, is the x-axis, right? Y equals 0. But then where does that change? At the halfway point. So I got to do the integral from what x to what x? 0.5, y 0.5, because that's where things they just change. They fundamentally change. The change functionally change. The function is now new. It's a different function. So from 0 to 0.5, x squared is definitely on the top. Minus 0, that kicks ass. So from 0 to 0.5, it's just going to be the area under that curve. And that's the straight up normal integral, right? That's what the integral does, kick ass. Plus, from 0.5 to 1, what's on top? X squared. What's on the bottom?
2x minus 1. So it's x plus 1.
Cool. I'll take that away. How does G go? No, it's good. You just see how I had to think about that. It's all about this way, but top and bottom changes on either side of this. So my first integral goes up to that because that's a definite. It's defined to be between these two functions. At 0.5, now it's defined to be between that function and another function. So I have to break the interval up there. Okay, maybe it's the kind of thing you look for over the interval that you're integrating. Does something change? Does another function take over somewhere? That's when you have to break the interval up. Okay. That's a good question. That problem's freaky because you got to take a minute and do old school stuff. Well, earlier this semester stuff. Just to get one of the walls defined. Right, so it's a semi-equal problem. So I'd like that, wouldn't I? Yes. Anything else from homework?
When they give you 3 walls, they usually have to set up.
So
you're most likely going to have to set up 2 integrals when they give you 3 walls.
It's normal. But what's nice with this one, they could have been even more evil, and they could have said from 0 to 2. Because then what happens then is this is now on the top and that's on the bottom. Do you see that?
Yeah.
Or possibly, in this case actually that wouldn't happen, but they could include in their intervals somewhere where the functions kind of cross. So it could be another function takes over, and then maybe further down the road 2 functions cross, and then that would require another interval to be set up. So that's 2 reasons why you have to set up more than one integral is another function takes over, so you got to set up an integral with that function in it. Or the 2 functions you work with cross over the interval that you're interested in. So if I had a setup like this, if I have a function, happy function, and I'm going from, let's say, A to B, and I have another function come in and it does like this, woohoo, right, and whatever. So that means that from A to this point, the black line's on top. So the integral of this minus that. And then after that, I have to set up another integral, purple minus black. Right? I mean, that's another reason why you have to set up more than one integral. So this is the same 2 functions, they just cross in the middle of the interval that I'm interested in. Or another function takes over. Oh shit, that's an obvious place I gotta have a separate interval.
On 6.16, is the x equals pi over 2 and x equals pi, are those some limitations, or are those, like...
Yeah, that's part of the,
Like it's only from...
Oh, there it is. That's part of the, those are part of the walls. So, that's a good one to try to set up here. This is number 6. You got y equals sine x, y equals x. So by itself, that's not good enough. Let's see why. So y equals sine x. Yeah. Let me give some definitions here. What point is that? When is sine biggest? Let's do that.
2 pi 0. You get 1 pi over 2.
I feel like the Indian, old.
Pi over 2, yeah.
Pi over 2. Sine likes pi over 2 because sine likes y, and 90 degrees is where it's all y. So what's that?
Pi.
So what's that?
Pi over, negative pi over
Negative pi over 2.
And negative.
Negative pi. Let's see if that's enough. And then y equals x. Now what's interesting is, where does y equal x cross this? Well, what is pi divided by 2?
Pi, so it's 1.57.
1.57. I like it. So, so 1 would be back here somewhere, right?
Yeah.
So 1 is about right there. So it looks like y equals x is going to cross somewhere between here. So I want to probably blow that up. Do you guys kind of follow what I'm saying? So a good first step would be to see where do these cross. But they also tell me, now let's see what else they tell me. They tell me pi over 2 and pi. So that was why I put that. There's a reason I put that. So pi over 2, x equals pi over 2. So this is a wall here. And that's a wall there. So this is getting interesting. And so, how do I say this? Y equals x is going to be where? So y equals x. So this is getting really strange. This problem. Yeah, they're just making it weird. Let's see.
Slant testing, that's right.
Okay. Y equals, okay. So here, this is going to, y equals x would be at about 1.5, right? Because that's about what that is. Is that cool? So it'll be, so y equals x would be about there. So here's y equals x. So there's my wall. So let's see. What's contained between all these walls? This is a very strange region, but oh well. There's a wall. There's a wall. So this seems to be the region I'm talking about. That region right there. Cool. And what's beautiful about these is they set up my limits. Yeah. So that one, they gave me the limits of my. I didn't have to figure out where the functions cross. I didn't have to do that work because they told me what they wanted me to do it across, right? From pi over 2 to pi. And so which function's on the top? Yeah, exactly. So it'll be integral, pi over 2 to pi. X is on the top.
Minus sine x.
Sine x is on the bottom. Bam. I like it. But see, I'm always looking, where do all the walls meet? And then what's in the middle is what my region is. So we've seen a couple examples where the book defined a weird region, but still, there's my region. That must be it. Anyway. Now let me make this a little weird. All right, that would be, you just have to do that to finish this problem out. You with me? Yeah. All right, let's look at a problem that Jeff might give you. Jeff would say, everybody got this if you want it? Okay.
Yeah.
Jeff would say, rotate this region around. No. Let's say rotate around y equals, let's say x equals 1. Ooh, I like it. It's yummy. So why did you say that?
If you do the rotation, you could make something out of it. That's why I would do it.
Okay. And I can kind of naturally see like a little rectangle setting up there.
Yeah.
What would discs require? Since we're doing around x equals 1, so x equals 1 is about right there. I'm going to rotate around that. Discs would need it to be integral dy. Do you really want to involve inverse sine?
No.
I don't want to solve these for y. I mean, do you see how
That's
there's several different ways to tell which method to use when? And one of the most fundamental ways is, can I or do I even want to solve in terms of this variable that this method requires? No. Okay, good. I'm not going to do it that way then. I'm going to do shells. Right? And so here's going back to the earlier question. When I'm setting up my shells, I want to draw in a representative rectangle for myself, right? So since I'm going this way, will my rectangle be standing up or laying down? Standing up. I want it to be parallel. I want the rectangle to be parallel lengthwise to how I'm rotating, right? So I'm going to have this little way, and I'm going to rotate that bad boy and make this shell. So I need it to be like this, not like that would be if I was rotating on the x-axis, if it's laying down. I want to go around this axis, so I want it to be standing up. Cool. And now right there, it's screaming at you what the height of it is. Right? So what do I need? I need 2 pi, I need the radius, I need the height. And of course I got my dx for my... So what's the radius going to be? So where is this rectangle? It's on the x-axis, so it's at x, but what's the radius going to be then? What's bigger? Is x or 1 bigger? X is bigger, so what's my radius going to be? X minus 1. Alright, let me stop right there. Let me just stop. Let me just stop. A rectangle, where the rectangle is, does not give a shit where the rotation axis is. The rotation axis will be way down there, and I'm still going to locate it x. Whatever x is at that spot, that's where the rectangle is. Then I say, well, what's my radius? Well, it's how far that rectangle is from the freaking axis. That's what the radius is. It only makes sense. It's the middle. I'm going to turn around it. So how far is that? X minus 1. It's less distance than if it was going to 0. So it makes sense that it's smaller than x. It's x minus 1. What's the height going to be? What's the height of that rectangle? What's the top? I took it away. Did I take? Oh, no, it's right here. X. Yeah, it's exactly the same as what was in the integral we were doing for the area between the curves. Right? And very often it will match with that. See, so shells is very much like what we just did. It just also adds on top rotation. So I start with a rectangle like I would have normally with normal integration, and then we do this weird shit to it because we're going to rotate that bad boy. Right? So it feels a little bit like what we were doing before. Sort of related to your question earlier, which I actually forgot, but I knew this was going to be related to it. Your question was, I can't remember. It's easy. When you draw the rectangle in, what got me here though? I have to know if it's standing up or laying down. If I said it was laying down, I would erroneously think it was from pi to pi over 2. I think that would be the height, right? Oh shit, that would be bad for me. So I'm standing it up because I want it to rotate like that. It's got to be parallel to how I'm rotating it. Standing like that going, oh, you know, rotating around. I'm trying to convey to you what I have in my head. That's basically what teaching is. So that's the height of the rectangle, is the distance between those two functions. So anywhere I put this rectangle, that's taller because the distance between these two functions is bigger at that x, whatever that x value is. So how do I put this all together? I got 2 pi integral. I know it's going to be dx, right? Everything's on the x-axis where my rectangles are. So it's from what to what?
From
Pi over 2 to pi. I knew that from the beginning, right? Pi over 2 to pi. Radius, x minus 1. Height, x minus sine x. Now this one actually, this would be funny because you can't do that. Oh well, too bad for us. So this might be one in the homework where they say use your calculator to do this. Can you guys like, how do you see that, Jeff? Because I'd have to FOIL this out, and am I not going to get x times sine of x? And if you think about it, can I integrate x sine x? We cannot integrate that yet. John's like, I'm not idiot. It's because you taught yourself the first method you learned in 280. So I'm not going to require you to do that. So there are some problems in the homework that say, do this in your calculator. Plus, I just made this one up off of some other problem. So who knows how it's going to show up. The other way, if I try to make it using disks, it would just be disgusting. Integrating the arc sign, I don't want to do that. What's most important here is how to set this thing up. That's what's most important. That's where most of us are having the trouble. Okay. Let's see. Anything else?
Yeah. 6.1, 21.
As far as tangent goes, why is this choice good? Let's see if you guys understand that question. Where does tangent have trouble? Where does tangent have issues? It's got issues, doesn't it? Tangent has issues. Functionally, it has issues. Issues with functions means either they're undefined or they go to freaking infinity, and that happens where? Fundamentally, it happens at negative pi over 2, for the representative cycle of tangent. You guys with me? It's going to happen every multiple of that afterwards. You guys remember that stuff? Okay. So they chose boundaries for my area to be inside there, so it doesn't include that. I can't integrate something if it goes to infinity somewhere in the interval. Alright, so they gave me an interval that's in between negative pi over 2 and pi over 2. That's going to be nice. That won't be a problem. So now I just got to really know, is one of them always on top, or do they cross somewhere? That's what I need to figure out now. And one way to do that directly is I know what's going to happen, because what does sine look like? What does sine sound like? Sounds like a lightsaber, actually. Alright, my scale obviously is, but who cares? And then tangent, of course, here's negative pi over 2 and pi over 2. It lives in, and then here's negative pi over 3 and pi over 3. Who cares? But tangent, of course, comes in and it looks very cubish, right? So tangent's going to come in. So what we're interested in is, where does it hit here? So here's negative pi over 3 roughly. So it's going to come in, and it's going to do that, and it's going to be in between those. I can't remember how to pronounce this, but we got to find these places. So it's definitely going to cross at 0.
Yeah.
There's no question about that. And then it looks like it might cross outside of there. But to verify that, so how do I find those places where that happens? How do I find those places? We know. Set them equal to each other.
Tangent x is sine x.
Yes, cool.
So sine x and sine x cancel each other.
Well, sort of. As long as, so the best way to do it is to bring it over and factor, but as long as you say sine x equals 0 as an answer, right? And of course that gives me what? X equals sine, where's sine 0? Where's sine 0? Pi, sure, but that's outside of my region, right?
Yeah.
0. Alright. Let me stop there for a second. You guys understand that? You don't want to just kill it because you're losing an answer then. It's like saying, x squared equals 5x, and just canceling an x out and say x equals 5. Well, you lost the answer of 0. 0 was an answer to that original equation, wasn't it? So if you ever cancel a variable expression, you're losing possible answers. Well, as long as you say, well, there's the answer that would have given me, now you can kill that as much as you want to. You're not losing anything because you collected it. So that's a way to do it without having to factor. You just identify what answer it would be, kill it. So then what do I get? I can say this is 1 equals
So 1 equals 2 cosine x,
So cosine x equals,
1 over 2,
and where's that happen? Where's cosine 1/2?
pi over 3, plus minus pi over 3.
Yeah, it's 60. Again. This is why I wish to God they would teach you cosine length x. So the further away from the x-axis I get, I'm trying to do this for you. This is 0 degrees, right? The further away from that I get, the smaller cosine is. So at pi over 3, it's really far away. It must be 1/2. It's gonna be really tiny. It's like, oh shit. So in here, it really doesn't like it, right? So it's 0 there. Like maybe. If they would just teach it that way, it's much better than SOHCAHTOA. SOHCAHTOA works this far. Cosine likes x, sine likes y works for a freaking ever. Anyway, sorry. I'll get over that someday. So this is be plus or minus pi over 3 is what I'm interested in, because that's exactly, so there you go. So this is negative pi over 3. This is pi over 3. Well, that's nice of them. So back here, according to my picture, we can verify this, but who looks to be on top back here?
Sine 2 sine x.
Tangent.
Tangent,
Right?
yeah.
And we can verify that. Again, I don't necessarily completely trust my picture, necessarily. So here, what's below pi over 3? Pi over, what's smaller than pi over 3? Pi over 4.
4.
So what's tangent of pi over 4?
1.
Oh, and of course I forgot the 2, didn't I?
Sure did.
I totally did. See, that's why I shouldn't trust my picture. So tangent of pi over 4 is what?
1.
1. And what's twice sine pi over 4?
Square root of 2.
Square root of 2. Which one of those is bigger?
Square root
So now I'm looking over here, actually. I'm not doing the negatives. So I'm looking at pi over 4 here. So my picture is correct. The sine is on top, the tangent's on the bottom. Why am I doing that? Because I've got to find the area. How do you think the areas, this area relates to this area? Equal. Because these are both odd functions, right? I don't know if you see that. If you don't trust that, don't do it. But you could actually integrate from 0 to 2 and double it. Because that area has to be the same as that area. They're created the same way. Yes? Maybe no?
Yes.
You all got together and said, don't give him anything. Don't give him anything to go on. Okay. Alright, and again, this is just me showing an example of picking a number in between so I can see who's on top. So of course back here it's going to be the reverse. For negative pi over 4,
Negative 1.
negative 1,
Negative.
negative root 2. So now the sign is below because that's more negative. Right? So if you wanted to do it all the way across that whole interval, where would you go? You would start from negative pi over 3 and go to what? Why go to 0? Why would you go to 0?
Yeah,
Because that's where they cross. That's where things change. That's the whole idea. Where you have to set up a new interval where things change. So negative pi over 3 to 0. And who's on the top here?
Tangent.
Tangent. So I would say tangent x minus 2 sine x. Plus 0 to pi over 3.
So it's
Yeah.
2 sine x minus
2 sine x minus tangent x. And my claim is that this is the same thing as twice this one. If you do both of these, they'll come out to be the same amount. And when you add them, you get double one of them. This is why pre-calc was supposed to get you had to do really detailed graphs in pre-calc so you're able to do rough sketches here in calculus. Right? For these problems, you don't have to do perfect sketches. You have ways to kind of check yourself, but the sketch gives you an idea of what's going on. So you have to be able to make decent sketches. You can back it up with actually doing some work, but the sketch is freaking important. Alright, anything else from homework before I move on to this? Today's Wednesday, that's right, it's not as evil. So this, like I said, I took this right off of an old final I gave in calculus. I think it was back in 2007. So you guys were in 5th grade? When you get older, it's like 10 years ago is nothing.
I wasn't even born at
Oh, I'll see you. Well, Doogie, how's it see you?
John. Thank you.
Sure.
Or you got it at 20.
So number one is from that last section we did, the average of a function. So if you want to skip that for now, you can. Number 2, 3, and 4 are all about finding volumes. If you guys want to work together, it's not a bad idea.
You did subtraction?
So I think what I'll do, number 2, go ahead and try to set